Okay, thanks everyone for we just have an assignment. I wanted to start with some ideas about question 4. Let me write down question 4 for you. I see I am probably leaving people out. There we go. Okay, let me write down question 4. It says, oh yeah, this is the assignment 1. It says, let A be a set, prove that there exists X such that X is not an A. Oh, am I not? Okay. Okay, if you're not seeing, I'm not exactly sure how to fix that. I guess you could try to put it on speaker view and look for, oh, or try that. Okay. So let's try and do this. Okay. I guess before we start this, I want to ask, does anyone, I mean, we only have what I guess axioms to work with. Does anyone want to suggest an idea of how to get started? There's different ways to do this question, of course. Let's see. Yeah, we need to find, yeah, that's a good start. We need to find some B on an A. If we do that, then we'll be done. That's a good point. The question, it doesn't say it has to be a set, but actually, at least the only proofs I can think of, the thing you find will be a set. So, okay. Okay, does anyone know of a or if even if you have a vague idea I'll just wait for like 1 or 2 more minutes. The complement of something. Yeah, so for the complement, it's a good idea. In a way, that will be the answer. So let's kind of divide our page in half because we can do it by contradiction as well. Let's do it by contradiction, and then let me read this other message. Yeah, okay, so yes, that is, yeah, it is like this question is just a trick. This is like, this question restated. Okay, so let's do it by contradiction, and let's do it with this, and it'll kind of explain to us that this is really, this question is really about Russell's paradox. Okay, let's do it by contradiction first. Is straightforward. So let's do it by contradiction. Assume for all x, x is an A. Okay. Let B be all the x's in A such that x is not in X. Okay. If B is in B, then B is not in B. If B is not in B, then B is in B. That's a contradiction. So there exists x such that x is not in A. Okay. I didn't go through this argument again because this is just like a repeat of Russell's paradox, right? So another way to state this question is, you could state it like there is no universe, no universal set, because if there were, this argument leads to a contradiction. Okay, but you don't even need to. You can do it just kind of the regular way, which would be this way. Just start out with this set. This is a fine set. And just prove that B is not in A. Okay. This is a perfectly normal set. This is a property. This is A is a set, so we get the set B. Okay. So now let's prove that B and so we don't really avoid contradiction, but oh well. By contradiction, if B is in A, then this usual thing happens. B is not in B implies B is in B, and B is in B, that implies B is not in B, and that's impossible. So B is not in A. Okay. So this set B, all the elements of A that aren't elements of themselves, gives us our set that's not in A. Okay. Okay, and that is question 4. So this question is just Russell's paradox, but slightly disguised. It was kind of a trick. Okay. I also wanted to do question 2. At least talk about it. Question 2. You have 3 sets, A, B, and C. And then basically the question tells us to construct the unordered pair ABC. Okay. And let's think about what tools we have. We have unions, we have unordered pairs, we have comprehension, that might be useful, things like that, okay? And I'll say there's definitely more than one solution for this. Let's try and work out at least one. Okay. So, okay. Yes, I was just going to ask you guys to suggest something. This question does resemble the axiom of pairing, except instead of pairing, it's like if there was a word for, I guess, I'm not sure, tripling, but not that, something else. Okay, but 3 things instead of 2. Okay, so let's start by using the axiom of pairing. It doesn't get us all the way there, but it gets us pretty close. You know, by axiom of pairing, we have sets A and B. We have AC. What else do we have? We also have BC. These are all sets. You have A, B, C. And by applying the axiom of pairing in different ways, we get all these different sets. Okay. Which is good. Okay, but we're not quite there yet. Does anyone want to suggest what to do next? I'll tell you. Power sets. That is possible. Use the axiom of pairing again. Both of these, I think, will work because a lot of different things will work. I think using the axiom of pairing again is, I think, easier. So let's try that. There's a few different things we could try. Let's pair these two. We could also pair these two or these two. I mean, there's a bunch of different things to try. So by axiom of pairing, these are all sets. So by axiom of pairing, another set is this set. And my two things are this set and this set. Okay. And now, now we're kind of getting somewhere because now it's clear that I should use the axiom of union. And if we do this, okay, the axiom of union is the set of all things X such that X is in AB or X is in the singleton C. Okay, if we think about all the things that are in this unordered pair combined with the set of all things in the singleton, well, this means X is in A or B or C. Or sorry, we have X is in the unordered pair, so X equals A or X equals B or X equals C, right? So we just need one more line. But what does X is in A or B? AB mean? That just means X equals A or X equals B, and X is in C. That just means X equals C. So that means that the union of the set, this is just the X's such that X equals A, B. That's the set we want. And we're done. Okay. So it is kind of awkward, especially this notation with unions. It's kind of weird, but if you do a few examples, if you get used to it, it's okay. Okay. Yeah, so so you can use, so the other way to do it, or there's probably other ways to do it, but another way to do it, alternately, look at the power set. I think No, I'm not sure. I don't remember how to use the power set. I think I remember there being a way. That's okay. So I wanted to still do another question. I wanted to do some of the things from proposition 1.16, just so that theory. So this would be question 6. And let's prove, like, for example, let's prove C minus A intersect B equals C minus B. Okay. And we just have 3 minutes. Oh. Okay, so this is just like this really and truly is from like first-year sets and numbers. But let's just try and remember. Okay. Let X be in C minus A intersect B. The second part, well, luckily for this kind of thing, if it is an intersection, we'll find out when we do the proof that it should be intersection. If it's really should be union, the proof will be right, you know? So if it turns out it was supposed to be intersection, we'll come back and fix it. Okay. Luckily, there's like no danger. If I'm wrong, then everyone will see that I'm wrong as we prove it, you know? Okay. So this just means that X is in C and X is not in A intersect B. Okay. So now we can split it up into cases. So either X is in A or X is not in A. Okay, so the first case we'll deal with is X is not in A. Well, if X is not in A, remember we have X is in C, so X is in C but not A. So X is in C minus A. So therefore, X is in C minus A union C minus B. Okay. The other case is that X is in A. Now we ask ourselves, is it possible for X to be in B? If X is in B, then X is A intersect B. This is a contradiction.